Hello everybody out there working on the linear programming intro. Hopefully you and your group had a productive conversation. Here we'll discuss how to work the math into this example. Because at first it probably seemed relatively simple. Well, how many of each bag should you sell to maximize your profit? Well, you should sell 1,000,000 of each bag, or maybe 10 million of each bag. That would give you quite a bit of a profit. So hopefully your answer to the first one was, really as many as you can. But then right away you see, oh no, there's only space that I can store 200 bags of coffee in pot A. Well, from there you probably decided, well, I should probably sell 200 bags of the Harvest Blend because the Harvest Blend gets me the bigger profit, so I should sell more Harvest Blend than, well, I should sell all Harvest Blend because I get the biggest profit out of that. But then again, now you found out that, well, you can only purchase 100 bags of Harvest, and the maximum number of choice bags you can purchase is 170. So that might change your answer again. Maybe your answer is, well, I should go ahead and buy as many Harvest as I can, or I should sell as many Harvest as I can, and sell the rest choice. That probably makes sense. And in the end, you can do this example this way. But I picked a fairly simple example to start with to show you a more challenging concept called linear programming. So I'm going to show you the steps of linear programming by using this example. And here we go. So we're going to go over here and talk about the steps to solving a linear programming problem. So linear programming will help you maximize or minimize some quantity within a set of constraints. This problem specifically asked us how many bags of each type of coffee the prom committee should sell in order to maximize profit. So linear programming will help us maximize our profit given the constraints that we had. A good next step is to define your variables, because we are going to be trying to find things. We're going to try to find how many bags of each type of coffee that they're going to sell that will give us the maximum profit. So let's have our variables represent those types of bags. So we can have X represent the number of bags of the choice blend, and we can have Y represent the number of bags of the Harvest Blend. You could have used H and C here if you wanted as your variables. That's fine. I just chose to use X and Y. Okay, next big step here is to write the objective equation. The objective equation is going to represent whatever it is that we're trying to maximize or minimize. And since in this situation we were trying to maximize profit, our objective equation should represent profit. Now if you look back at the original problem, the profit comes from $3.50 for every bag of choice we sell and $4 for every Harvest Blend bag we sell. So a good equation for that would be $3.50 times X, the number of choice bags, plus $4 times Y, because that's the number of Harvest bags we sell, times the profit we get for each bag that we sell. So this equation represents profit for us in this situation. We're actually going to set this aside for a while and go with now we're going to start dealing with the constraints that are involved with this problem. So, if you think about this equation, well, in order to get the biggest profit possible, it'd be nice to plug in 1,000,000,000 right here and 1,000,000,000 right there. That'd be quite a profit for us. But again, as we mentioned earlier, we have some constraints involved. And these constraints are going to keep us from having 1,000,000,000 bags of choice and 1,000,000,000 bags of Harvest. So that's what we're going to deal with next, is we're going to deal with these constraints. Now one of the constraints specifically said that we can hold no more than 200 bags of coffee in pot A. Well, that sounds like a perfect setup for an inequality. So if I were to add the choice bags plus the Harvest bags, they better be no more than, so less than or equal to 200. That tells me, okay, when I add up the however many choice bags plus however many Harvest bags I have, I better have less than or exactly 200 bags of Harvest or of coffee. Now we also found out that we can have no more than 100 bags of Harvest and no more than 170 bags of choice. So those are two more inequalities for us. We've got one now that says X, so that's choice, has to be less than or equal to 170 total bags, and Y is going to have to be less than or equal to 100 total bags. And again, each of these constraints slash inequalities came from the wording of the problem. So remember, in the wording of the problem, you had the fact that you could have at most 200 bags of coffee, so x plus y is less than or equal to 200. You were also told that at most 100 bags of harvest, so y has to be less than or equal to 100. And you were also told that you would have at most 170 bags of choice. So that's where these inequalities came from, directly from the wording of the problem. The next step is going to be for us to graph our constraints, and then we're going to find the coordinates of the corners of the region that we're going to create within these constraints. So the graphing comes next. To graph these inequalities, I have chosen a scale of, I'm counting by tens, because I know I need to get up to at least 200. 200 is the total number of bags I can have altogether. I've got my x-axis labeled as the bags of the choice brand because we had defined x as the number of bags of the choice brand, and y is the number of bags in the harvest brand, so that's why my y-axis represents the harvest brand. And so we're going to go ahead and put these inequalities on here. Now, the first two are relatively easy. Not the first one. The first one's the most challenging. Let's do the second two first. The second one says x is less than or equal to 170. X is less than or equal to 170. Well, an x equals line will be a vertical line. So I go over to 170, which is right here. I do a solid vertical line going up. And this indicates that I should shade things that are less than or equal to 170, which means when it's time to shade, I'm going to go ahead and shade to the left. The second inequality or constraint was y is less than or equal to 100. So that's going to be a nice horizontal line at 100. So I draw that right at 100. And this indicates that I'm going to want to shade everything below that line. So when it comes time to shade, I'm going to shade below the line there. Now, I'd say the most challenging of our constraints, our inequalities, was the one that was labeled x plus y has to be less than or equal to 200. Now we can easily graph that. We're just going to get y by itself. It says y is less than or equal to negative x plus 200. So that's not too bad. We're going to start up at 200 as our y-intercept. We've got a slope of negative 1, which means we're going to go down 1 over 1, which really is the same idea as going down 10 over 10. So we're going to keep going like that. And if we continue to go down 1 over 1 forevers, we should end up over at 200 on the x-axis as well. Now, again, we've got the symbol here that indicates we are going to shade below this line when it comes time to shade. So we're going to shade below this, and there we go. Now, one thing you may not notice, or maybe you have noticed, is that I really have kind of secretly graphed two other inequalities as well. I didn't put them on here, but I probably should. We're going to leave x is greater than or equal to 0 and y is greater than or equal to 0 as constraints as well. And this is because you cannot have negative bags. So it's kind of secretly implied in there that we're not going to go to the left of the y-axis or below the x-axis. We're going to stay to the right of the y-axis and above the x-axis. So if you are solid at graphing inequalities, you'd recognize that this here is our region. This here is the region that includes all of the potential coordinates that fit our constraints. These are all the potential coordinates that make sure that x is less than or equal to 170, y is less than or equal to 100, and that when I add up the total number of bags, I am not over 200. That's what this region represents here. This region has a name. This region is called the feasible region. Now we could go through and find and take every single point that's in this feasible region and plug that into our objective equation and see which one gives us the biggest possible profit. Because again, all these points here represent points that meet all of our constraints. So yeah, we're not going to be able to plug in 1 billion for each bag, but we can plug in, up to a certain amount of each bag here. And our goal is to find out what combination of harvest and choice bags will give us the maximum profit. So again, all these points within this highlighted region meet the constraints. I could plug all of them in and see which one gives me the most profit. But you only actually have to try certain points. All you have to try are the corners or vertices of this feasible region. So it's important you know what the corners or vertices of this feasible region are. This one is real easy to see on this. This one clearly is the coordinate 0, 100. This one here will be 100, 100. Down here, this one looks like it is 160 and 30. Take that back. That appears to be 170 and 30. And then the bottom corner of our region is apparently has the coordinates 160, 0. Oh, and then I have 0, 0 here as well. So these are the only 1, 2, 3, 4, 5 points I need to plug into the objective function, the objective equation, to figure out which one will give me the maximum profit. So that's what this next step says to do. So again, remember the objective equation was that profit equals $3.50 times every bag of choice blend we sell plus $4 for every bag of harvest that we sell. So now all we got to do is take each of those corners and plug them in here. Now, you can try the bottom left-hand corner, which was 0, 0. Is there any need to plug that in? That's going to give us a profit of 0. Clearly won't be our maximum profit, so that's not going to be too much work for us. Now let's try the top left corner, the one that's at 0, 100. So when I plug in the corner 0, 100, that means I have 350 times 0 plus $4 times 100, which means my profit will come out to be $400. Maybe that's the most. Who knows? We'll find out next. Now we're going to try the point 100, 100. So we have 100 for x and for y, which means I'm going to go $3.50 times 100 plus $4 times 100. Leaves us with $350 plus $400, which gives us $750. That's our profit there. Next point is going to be 170, 30. So that means we have $3.50 times 170 plus $4 times 30. I know this will be 120, and let's see. This turns out to be $595. When we add those, we're going to get $715 for our profits. So still, this one appears to be the winner. We have one more point to try, and that's the point. Oops, appears I also made a mistake on this one. This should have been 170, 0. So we're going to do x. We're going to do the point 170, 0, and we'll find out that our profit there equals just the 595. Okay, so as we look at the profit coming from each of these corners, we find out this is the biggest profit, which is again what you had figured out hopefully originally, but now we have some math behind it as well, additional math behind it. I'm sure you had some solid math behind it when you said it originally, but hopefully this process helps you understand how to work linear programming problems, because that's what the rest of this week's going to be about. So the final part is to answer your question in a complete sentence, and we will tell the prom committee that they should sell 100 bags of choice and 100 bags of harvest to get a maximum. They should sell 100 bags of choice and 100 bags of harvest to get a maximum profit. Now it won't always be that X and Y match like they did in this one. It just happened that they were both 100. But this is the way. This is the process. So this is the process for solving a linear programming problem. Hopefully you can refer back to this video as we get into more challenging examples.